In this video, you'll see exactly how long it really takes to go to the moon and come back on a real mission, step by step, from launch to landing to splashdown, and why the real number is very different from what you probably think. First, let's pin down the basic number. The average distance from Earth to the moon is about 384,400 kilometers, which is roughly 238,900 miles. That's the value you see in textbooks. But the moon's orbit isn't a perfect circle, it's slightly stretched. At its closest, it's around 363,000 kilometers away, about 225,000 miles. At its farthest, around 405,000 kilometers, about 252,000 miles. So there's already a swing of more than 40,000 kilometers, over 25,000 miles, just from where the moon is in its orbit when you leave. Now, translate that into something your everyday brain understands. Let's say you drive at 100 kilometers per hour, about 62 miles per hour, and you never stop. No sleep, no food breaks, just a constant boring cruise. To cover the average Earth-Moon distance once, you'd be on the road for close to 160 days. That's more than 5 months just to do one way. So when you look up at the moon and think, it doesn't look that far, your eyes are lying to you. In human travel terms, it's extreme. So if the distance is that huge, how do we end up casually saying 3 days to the moon like it's just a long flight? That's the first thing we need to straighten out. When people say about 3 days, they're not talking about some universal cosmic rule. They're talking about a very specific type of mission profile. Crewed Apollo-style trips using big chemical rockets and a standard transfer trajectory. Here's how that actually works. You launch into low Earth orbit first, roughly 200 to 400 kilometers up. Once you're parked there and the systems are checked, you fire your engine in what's called a trans-lunar injection burn. That burn doesn't point you at the moon in a straight line. It reshapes your orbit around Earth so that the farthest point of that orbit reaches out to where the moon will be. For Apollo missions, the time from leaving low Earth orbit to getting captured by the moon's gravity and entering lunar orbit was typically around 72 hours, so about 3 days. That's where the famous number comes from. You're not blasting the whole way, you're doing one big push, then coasting on a precise path set by orbital mechanics. You accept those 3 days because they give you a good balance of fuel use, safety, and hardware complexity. Now here's where your expectations really start to bend. The fastest spacecraft to cross the distance between Earth and the moon's orbit was not a moon lander, not even a lunar orbiter. It was the New Horizons probe, the mission that went to Pluto. That spacecraft left Earth so fast it passed the moon's orbital distance in about 8 hours 35 minutes. It wasn't trying to stop at the moon, it was on a one-way high-energy escape path out of the inner solar system. No life support, no crew, no need to slow down at the moon, just raw speed. On the opposite extreme, look at India's Chandrayaan-2 mission. Instead of one big high-energy push, it used many smaller burns to gradually raise its orbit around Earth, each loop higher than the last until the moon's gravity could catch it. That strategy saves fuel, because you spread out the energy. But it costs time. The trip from launch to lunar orbit took on the order of 48 days, so about 7 weeks. So now you've seen both ends of the spectrum, around 8.5 hours on the fast side, roughly 48 days on the slow side, both covering essentially the same Earth-Moon distance. That's a difference of almost 150 times in trip duration. Same physics, same basic target, completely different mission choices. That's your first big takeaway. How long it takes is not fixed by distance alone, it's heavily shaped by what you want the spacecraft to do. That leads to the real question you probably care about. You're not sending a robot that doesn't care about time or comfort, you're sending people and you want them back. So you can't just ask, how fast can we get there? You have to ask, how long does a realistic human mission take, including getting home in one piece? Once you put humans into the picture, the clock becomes a survival tool, not just a travel estimate. You have to think about safe acceleration limits, so the crew isn't crushed by too many G. You have to track radiation exposure because every extra day in space adds dose. You need enough oxygen, water, food, and power for the entire round trip plus margin for delays. You need trajectories where you can still abort and swing back to Earth if something fails, and you need to hit re-entry at exactly the right speed and angle so the capsule doesn't burn up or skip off the atmosphere. When you look at actual crewed moon missions with those constraints, a pattern appears. Apollo landings ran from about 8 days to roughly 12 days total, from launch in Florida to splashdown in the ocean. The upcoming Artemis landings will sit in a similar band, often a bit longer, around 10 to maybe 20 days depending on how much time they spend in lunar orbit, docking with other vehicles, and working near or on the surface. A short focused landing mission with modern tech is still going to be around 8 to 14 days for a full round trip in most realistic scenarios. So your moon trip is not 3 days there, 3 days back, simple math. That ignores all the time you spend parking in orbit, checking systems, orbiting the moon, doing surface operations, and then setting up the return. The real timeline is a chain of tightly scheduled phases, where every hour is allocated to either getting you there, keeping you alive, or setting up the next critical maneuver. Here's the plan for everything that comes after this. We're going to walk through that chain step by step, the way a mission controller sees it. You'll see how many minutes you burn just getting to low Earth orbit. You'll see how a single 6-minute engine burn locks you into a 3-day coast. You'll see why you spend days circling the moon before landing. And you'll see how the return leg is carefully shaped so that you hit Earth's atmosphere in a narrow, safe corridor. And there's a deeper tension underneath all of this. If the physics allow you to cross the Earth-Moon distance in hours, but human missions still sit in the 8 to 14-day band, what phase of the mission is really controlling that time? Is the limit your rocket, or is it everything wrapped around the rocket? That's where we're going next. Because before you even think about those 3 days to the moon, you have to face something slightly brutal. Most of the energy for your entire week-long mission gets spent in the first few minutes after liftoff, while your mission clock has barely started. So when you strip away all the hype and posters, how long did an actual flown moon mission take, down to the hour and minute? Start with Apollo 11, the first landing, because that's the cleanest baseline you can get. The rocket left Earth on the 16th of July 1969, and the crew splashed down in the Pacific on July 24th. Total mission time, 8 days, 3 hours, 18 minutes. That's the full loop Florida launch pad to the lunar surface and back to Earth's ocean in just over 8 days. In normal life terms, it fits inside a single week plus a long weekend. For something that crosses hundreds of thousands of kilometers, that's brutally efficient. And also a bit unnerving, because it means there wasn't a lot of slack in that schedule. But here's what you really want to know. How is that time actually carved up? Where are those 8 days hiding? The outbound leg is the first big slice. After launch, the Saturn V doesn't go straight to the moon. First, it pushes the spacecraft into low Earth orbit, a parking loop about 200 kilometers up. Once everything checks out, the third stage restarts and performs the trans-lunar injection burn, the shove that stretches the orbit out toward the moon. From there, the crew is on that curved transfer path for roughly 72 hours, close to 3 days before they drop into lunar orbit. On that arc, they travel around 400,000 kilometers, about 250,000 miles, but they're not doing it at the maximum speed you see at liftoff. Their average coasting speed over that leg is roughly 4,000 to 5,000 kilometers per hour, around 2,500 to 3,100 miles per hour, relative to the Earth-Moon system. It's much slower than the peak speed off the pad, but they can hold it for days without burning much fuel. One big kick, then 3 days of controlled fall through space. You feel like 3 days to the moon is a long time, but compared to what your car would need, it's already insanely fast. So they've spent about 3 days just getting to the moon's neighborhood, but they don't drop straight down to the surface the moment they arrive. Why not? Once Apollo 11 arrived, it spent at about 59 hours in lunar orbit before the landing. That's just under 2.5 days circling around 100 kilometers above the surface, running checks, tracking the landing site, confirming the guidance, and building in chances to abort if anything looks wrong. Only after that did the lunar module separate and go down. On the surface, they spent about 21.5 hours total, just under a full Earth day, from landing to liftoff again. Out of that, only about 2.5 hours were actually outside walking in their suits. The rest was getting ready, doing checks, sleeping, stowing samples, talking to mission control and making sure nothing had broken. Later missions stretched this dramatically. Apollo 17, the last landing mission, spent around 75 hours on the surface, more than 3 Earth days with 3 long moonwalks in a rover. The important part for you is this: the mission clock never stops just because the crew has arrived. Every extra hour in orbit or on the surface means more oxygen, more water, more battery power, and more exposure to risk. You might think, okay, but once they're done, getting home has to be quicker, right? Just point at Earth and fall back. It's not that simple. From the moment the Apollo 11 ascent stage fired and left the lunar surface to the moment the crew hit the water back on Earth, the return phase took just over 2.5 days. First they launched back into lunar orbit, rendezvoused and docked with the command module, transferred crew and samples, and jettisoned the ascent stage. Then they performed the trans-Earth injection burn, the mirror of the outbound burn, to drop out of lunar orbit and onto a path back to Earth. After that, it was another multi-day coast, with small corrections until they hit the atmosphere at around 11 kilometers per second and rode the re-entry corridor down to splashdown. So in rough numbers, you have about 3 days out, around 2 to 3 days back, and in between you pack several days of orbital operations and surface work. The flight time is big, but it's not the only player. The timeline is a sandwich, and the travel is just the bread around a thick filling of tasks that have nothing to do with raw distance. Now zoom out a bit. Was Apollo 11 some special short first try case, or did all the landing missions live in the same neighbourhood of time? Look at Apollo 11 through Apollo 17, the actual moon landing missions. They all sit in a similar band. Total mission durations ran from about 8 days at the low end to roughly 12 days at the high end. The ones that were closer to 8 days had shorter surface stays, fewer moonwalks, and simpler goals. The ones that pushed up toward 12 days were the science-heavy missions, more time orbiting, more time driving around with the rover, more samples, more experiments, more nights where the crew slept in lunar orbit instead of back on Earth. And here's the counterintuitive part that matters for your original question. The round-trip time for a human mission to the moon is not dominated by the time you spend physically crossing the space between Earth and Moon. That travel time is important, but inside a narrow design band it doesn't change that much. What really stretches or squeezes the clock is what you decide to do once you're there. How many orbits you fly before landing, how long you stay on the surface, how complex your operations are. If you doubled the surface time on an Apollo-style mission, you didn't double the distance, but you did push the total mission length up by days. And if you tried to shave a day off the 3-day transfer by going a little faster, you'd pay a high price in extra fuel and tighter margins for a relatively small gain compared to just trimming a day of surface work. So when you ask, how long would it take to go to the moon and come back on a real mission? Apollo already gives you a clear answer, and a warning. Expect something like 8 to 12 days because that's where real flown missions land when you balance safety, science, and engineering. And if you want to move that number, you're not just tweaking speed, you're cutting into what the crew can actually do there, or into their safety margins, which sets up the next, sharper question. If the total round trip is only about 8 to 12 days, why does the mission effectively bet your life on what happens in the first 10 minutes after launch? How can a mission that runs for more than 200 hours lean so hard on what happens in the first 10 to 12 minutes that if you mess those minutes up, the rest of the timeline doesn't even exist? Your trip to the moon does not start by dealing with the moon at all. It starts with a brutally simple requirement: get into low Earth orbit. Not high orbit, not halfway to the moon, just a loop around Earth about 200 to 400 kilometers up. In distance terms, that's about 0.1% of the way to the moon. It sounds almost trivial, like a warm-up lap, but in energy terms, this is where you pay almost the full price. To stay in low Earth orbit, you need to be moving sideways at around 7.8 kilometers per second, roughly 28,000 kilometers per hour, about 17,500 miles per hour, plus a bit more to cover drag and steering losses. You're not just going up, you're mostly going so that as you fall toward Earth, the ground curves away under you. That speed is in the same ballpark as a rifle bullet. but instead of lasting milliseconds, you have to hold it forever. Reaching that state is like crossing a huge entrance fee. Once you've paid it, everything else, including going to the moon, is adding smaller amounts on top. So how do you buy that speed in the first place? This is where the Saturn V comes in. On the pad, it was about 111 meters tall, around 363 feet, essentially a skyscraper full of fuel. At liftoff, it produced about 34.5 million newtons of thrust, which in imperial terms is roughly 7.6 million pounds force. If you like power numbers, we're talking on the order of tens of millions of horsepower being dumped into the stack in those early minutes. It's a controlled explosion pointed in one direction, and the only reason it doesn't look like chaos is because the engineering is insanely tight. Now look at what happens to your mission clock in that window. From T0, when the clamps release, to being safely in orbit, you're talking about roughly 8 to 9 minutes. In that time, the first stage fires for a bit over 2 minutes, drops away, the second stage takes over for another several minutes, then the third stage finishes the job and circularizes the orbit. By the time the engines shut down and you're coasting around Earth once every 90 minutes, the stack has burned through most of its propellant. Mass has dropped dramatically. Those few minutes are where the rocket equation really punches you in the face. Here's the strange part. You've used up the majority of your fuel budget for the whole mission, and yet in terms of distance to the moon, you're basically nowhere. You're a few hundred kilometers above Earth, the moon is hundreds of thousands of kilometers away, and still, from an energy point of view, you've already climbed most of the gravity hill. Everything after this point, all the way to lunar orbit, is about adding a bit more speed on top of that orbital base and then reshaping your path. Energy-wise, the curve is already mostly downhill compared to what you just did. You might ask, if the goal is the moon, why not aim straight for it from the start, skip this whole parking orbit step and go direct? Wouldn't that be faster? Direct ascent was actually studied. On paper you launch, burn continuously, and follow a more direct path that ends at the moon instead of in low Earth orbit. In practice, it's a nightmare. You have almost no pause to check systems. Every guidance error is harder to correct because everything is happening in one long, high-energy push. The rocket has to carry more fuel in one piece, which makes it even larger and more complex. And if something small goes wrong late in the climb, you have fewer clean abort options. Parking in low Earth orbit solves a lot of that. It acts as a staging area. You get into a stable loop first, shut the main engines down, and then you have time to catch up. You check the spacecraft systems, you verify that the guidance and navigation are working, you talk through the next steps, then you do the trans-lunar injection burn with a smaller engine that you can time more precisely. You trade a small amount of extra time on the order of tens of minutes for a huge gain in control and safety. So that first chunk of your mission, from launch to being quietly coasting in low Earth orbit, is your first real checkpoint. Timeline-wise, you're maybe 10 to 12 minutes past liftoff. The official launch countdown is over. The rocket noise is gone. From the outside, it looks like the exciting part just finished. But this is the moment where the serious clock really starts. Once you're in low Earth orbit, you're no longer sitting on the pad with support equipment plugged in. You're a closed system. Every kilogram of oxygen, water, food, and battery energy on board has to last until splashdown. Every gram of propellant left is all you get for trajectory corrections, for the burns to go to the moon, for the burns to slow down at the moon, and for the burns to come home. Think about the ratio here. A typical Apollo landing mission ran a bit over 8 to 12 days, so more than 200 hours total. In the first 10 minutes, you've already burned most of your fuel and locked in the basic performance of the vehicle. You've spent the hardest energy. If those minutes go badly, you do not get a chance to fix it later. There is no backup rocket waiting in orbit. The whole rest of the mission is built on the assumption that this first gate is passed cleanly. And that's why this phase feels so brutal. You've just compressed the most violent, high-risk, high-energy part of a week-long mission into a single-digit number of minutes, and now you're sitting in a quiet spacecraft, with Earth sliding underneath you every hour and a half. The tension doesn't drop, it just changes. The question flips from, can the rocket perform, to can we now use this orbit and the limited fuel we have left to hit the moon on schedule without wasting a single major burn? Because the next move, the one that actually bends your path out of Earth orbit and commits you to those approximately 3 days of deep space, is coming up fast. And unlike the launch, it's not something you can watch from a beach. It's a 6-minute engine burn on the far side of the planet that quietly decides whether your 8-day mission is even going to have a moon in it at all. How much pressure can you pack into one engine burn when 6 minutes of fire quietly decide whether you're going to the moon or nowhere at all? You're in low Earth orbit now, about 200 to 400 kilometers up, moving at roughly 7.8 kilometers per second, close to 28,000 kilometers per hour, around 17,500 miles per hour. That's great for staying above Earth, but it's useless for actually reaching the moon. To get there, you don't need to go higher in some vague sense. You need to stretch your orbit so that its farthest point, the apogee, reaches all the way out to lunar distance. That stretch is what the trans-lunar injection burn does. For Apollo, that meant restarting the 3rd stage of the Saturn V after roughly 1 to 1.5 laps around Earth. The crew checks out systems, confirms the trajectory, and when everything is green, the command is given. The engine lights, and for about 6 minutes it pours extra velocity into the spacecraft. Your speed relative to Earth climbs from orbital speed, around 7.8 kilometers per second, up to roughly 10.8 kilometers per second, more than 39,000 kilometers per hour, around 24,000 miles per hour. That jump in speed is not just going faster, it's the exact amount needed to put the high point of your orbit right where the moon will be days later. Too little and you fall short. Too much and you blow past. So at the end of those 6 minutes, you've done more than just fire a rocket. You've committed to a very specific future position in space and time. And that's where the tension really starts. Because once that burn finishes, you're no longer just in orbit. You're on a multi-day ballistic arc, a freefall path shaped by the gravity of Earth, the gravity of the moon, and your initial push. You can still change things, but you can't just stomp on some imaginary brake and turn around like a car. Any serious change now costs precious propellant, and big moves get expensive very fast. You've also stepped into the 3-body problem in a real practical way. Earth is pulling you, the moon is pulling you. You're moving fast through a constantly changing gravitational field. The math is complicated, but the bottom line for your mission clock is simple. You've basically locked in about 3 days of flight to reach the moon's neighborhood. You can tweak the details with small burns, but you're not getting a 30-minute oops, let's go back option anymore. Time-wise, that one burn has glued you onto a multi-day journey, whether you're feeling ready for it or not. Now here's the part that breaks everyday intuition. If you want to get somewhere faster on Earth, you keep pressing the accelerator. In space, you do almost the opposite. You fire once, then you coast with the engines off for days. That feels wrong at first, but it's how orbital mechanics works. Why don't you keep the engine running and just blast there in a few hours? Because the problem isn't that the rocket's too weak, it's that going too fast ruins everything else. If you crank the speed too high, you arrive at the moon's distance with so much excess velocity that you either miss it entirely, fly straight past on a hyperbolic path, or you have to burn an enormous amount of fuel to slow down enough to be captured. You'd trade a shorter travel time for a huge spike in fuel use and risk. The 3-day trip is tied to orbital geometry. You need a trajectory where the spacecraft and the moon reach the same point in space at the same time, with a relative speed you can handle with reasonable burns. The time is baked into the shape of the orbit you chose. You're not cruising slowly because you're lazy. You're cruising at exactly the speed that makes the rest of the mission solvable without absurd rockets and insane margins. So you do the counterintuitive thing, you light the engine for a few minutes, then shut it down, and accept days of nothing, while gravity and geometry do the hard work. And that nothing is actually packed with tension, because your options are now limited, and your safety net is mostly baked into the path you picked at the start. This is where the free return concept comes in, and where Apollo 13 stops being just a famous story and becomes a very precise piece of mission design. A free return trajectory is a special kind of path where, if you lose propulsion after the trans-lunar injection, you don't just drift into nowhere. Instead, gravity curves your arc around the far side of the moon, and then drops you back toward Earth automatically. No big engine burns required, just small corrections. The whole loop from Earth to the Moon's far side and back to Earth takes on the order of 6 days. Apollo missions often used free return paths early in the flight, especially before committing to more complicated orbits. That way, if the main engine failed or something critical blew up, the crew would still come home. Apollo 13 is the textbook case. An oxygen tank exploded on the way out, crippling the main service module. They couldn't do a normal mission anymore. But because they were on, and then adjusted back toward a free return style trajectory, they could use only small course correction burns with the lunar module's engine to stay on that loop. They never landed, but they swung around the Moon and came back in roughly 6 days total. The trajectory itself did the heavy lifting of getting them home, so that 6-minute burn at the start doesn't just send you toward the Moon, it often sets you up with your backup plan too. It decides not only how you arrive, but how you might survive if things go wrong. By the time the trans-lunar injection burn is done, the third stage is discarded, the spacecraft is reconfigured, and initial checkouts are complete. You're roughly 3 to 4 hours past launch. Think about that. In less than a single evening on Earth, you have gone from a rocket on a pad to low Earth orbit to being fully committed to a multi-day path across hundreds of thousands of kilometers of empty space, with a built-in minimum duration. From here on out, your mission is riding on celestial mechanics. You can't make it drastically shorter without paying a brutal price in fuel, hardware and risk. The clock isn't just counting down your oxygen and water anymore. It's also counting down to specific moments when burns must happen. Windows that last minutes, not hours, if you want to be captured by the Moon or get safely back to Earth. And that brings you to the next big pressure point. You've lit the big engine twice, you've stretched your orbit all the way out, and now you're going to spend about 3 days with the engines mostly off, drifting through deep space. But that drift isn't downtime, it's a 3-day stretch where tiny mistakes quietly grow into huge problems. So the real question now is, how do you live through those 3 days in deep space when the engines are quiet, but the mission clock and the physics are still moving at full speed? So how dangerous can 3 quiet days in deep space really be, when the big engines are off and everything is supposedly calm? Right after the trans-lunar injection burn, you're on day 1 of the coast, and Earth still has you in a pretty tight grip. In the first 24 hours, your distance from Earth climbs from a few thousand kilometers to tens of thousands. On a tracking screen, that looks impressive. The line stretches out fast. But if you look at your speed relative to Earth, you see it slowly dropping. You're climbing uphill out of Earth's gravity well, trading speed for altitude, and gravity is constantly pulling against that initial push. This part of the mission is where you clean up the trajectory, not where you show off with big burns. Those cleanups are the mid-course corrections. Instead of adding hundreds of meters per second, you're adding just a few meters per second here and there. Tiny nudges, a short engine pulse, maybe a couple of seconds, that slightly shift your path so that 3 days from now, you arrive a few kilometers closer to the target point instead of hundreds of kilometers off. The time in this phase goes into navigation, cross-checking your guidance systems, checking alignment with star trackers, and making sure redundancy actually works. Every hour is used to improve confidence in where you are and where you're going rather than to go faster. Move into day 2, and you're in the region that feels like no man's land between Earth and Moon. You're somewhere around halfway in terms of distance, maybe a couple 100,000 kilometers out. Here, the gravitational pull from Earth and the Moon becomes comparable. Earth is still the heavyweight, but the Moon's influence is no longer tiny. You're flying inside a shifting tug-of-war. To keep control of the situation, your navigation stack has to perform well. The inertial navigation system tracks accelerations and rotations, but it drifts over time. Star trackers look at known stars and lock in the spacecraft's attitude. Radio ranging between the spacecraft and tracking stations on Earth measures distance with signals moving at the speed of light. All of this together pins down your position to within kilometers while you're moving over hundreds of thousands of kilometers of flight. Here, the mission clock starts to include light time in a serious way. Radio waves take over a second to go one way at lunar distances, more than 2 seconds for a full round trip. That doesn't sound like much, but if you fire a burn on a stale measurement or react too late, you're correcting based on where you were, not where you are. So the timing of navigation updates, the schedule of when you send commands and when you read back data, becomes part of the safety margin. Day 2 is not visually dramatic, but it's where precision is either protected or slowly lost. By day 3, the balance tips. The moon's gravity starts to dominate and you begin to fall downhill into its well. Your speed relative to the moon rises again, climbing back into the range of several kilometers per second. The trajectory that looks slow and gentle on day 1 is now delivering you to the moon at dangerous speeds if you don't manage it correctly. If you let this run without intervention, one of 2 bad things happens. You either fly past the moon at high speed and end up on some unwanted path around the sun, or you intersect the moon on a collision course. To avoid both outcomes, you have a hard time constraint. You must perform the lunar orbit insertion burn within a narrow window, a slice measured in seconds to minutes, about 3 days after the trans-lunar injection. The spacecraft's position and velocity at that moment are not negotiable. They're the result of everything you did and did not do during those 3 days. Missing that window even slightly changes your orbit altitude, your inclination, and how much fuel you have to spend to fix it, if you can fix it at all. Now the obvious question hits, why not just speed this whole phase up? Why not make the trans-lunar injection burn much more aggressive, cut the coast to 1 day and be done? In principle you can. In practice, for a crewed mission, it's a bad trade. Pushing to a much faster transfer means adding several kilometers per second to your departure speed. That demands a much bigger rocket, more propellant, and a heavier, more complex launch stack. The G-forces on the crew during the burns go up, because you either accelerate harder or burn longer. Humans can handle a few G for a while, maybe up to around 3 to 4 G comfortably in a launch profile, but if you start pushing beyond that for long periods, you get into serious issues with blood flow, vision, and consciousness. Faster trajectories also squeeze your navigation margins. Any small angle error in your initial burn grows over time. If you're covering the same distance in 1 day instead of 3, your angular tolerances tighten and your correction windows are shorter. You would need even more precise guidance, more frequent updates, and more powerful correction burns. Add radiation into the picture, and the problem gets worse. A superfast trajectory that uses more time in high radiation regions or forces you to accept fewer abort options is not automatically safer, just because the calendar has fewer days on it. That's why for crewed missions, these 3 days of coasting are intentionally boring. They are designed to be calm with low activity on the engines, plenty of time for checks, and multiple opportunities to correct small errors before they turn into big ones. The point is not to wow anyone with the shortest possible transfer time. The point is to arrive with the crew alive, the spacecraft healthy, and enough fuel left to capture into orbit, land, and come home. By the time you're finally lined up for the lunar orbit insertion burn, you're roughly 72 hours into the mission. 3 days since launch. You've travelled about 400,000 kilometres, roughly 250,000 miles, across space. You have not fired a major engine since that initial 6-minute trans-lunar burn. Everything since then has been done with small corrections and careful navigation, and now the tension climbs again. You're moving fast relative to the moon, you've spent 3 days letting gravity shape your path, and you have one main chance to hit the brakes hard enough for long enough to drop into lunar orbit instead of just flying by forever. So the next question is simple but brutal. How do you slam on the brakes at the moon with one critical burn, while knowing that a timing error of a few seconds can be the difference between safe orbit and never coming home? You spend 3 days falling toward the moon, and then the whole mission hangs on a single burn, just a few minutes long, where you basically hit the brakes at orbital speed and hope the math was right. By the time you reach the moon, you're moving at several kilometers per second relative to it. If you don't slow down, you don't arrive, you just swing past on a flyby, and disappear into a new orbit around the Sun. So the first thing you do at the Moon is something that feels backwards. You flip the spacecraft so the main engine points in the direction you're moving and you fire it backwards, directly against your velocity. That's the lunar orbit insertion burn. For Apollo, that burn lasted around 6 minutes. In that window, the main engine shaved off roughly 900 meters per second of speed, nearly 1 kilometer per second. That doesn't sound huge compared to the 10.8 kilometers per second you left Earth with. But out here, that difference is exactly what shifts you from a fast, open trajectory into a closed loop around the Moon. Get it right, and you end up in a stable orbit about 100 kilometers above the surface, around 60 miles. Get it wrong, and you're either too fast and fly away, or too slow and dip toward unsafe altitudes. So the obvious question is, how tight is this timing really? Can you just burn around then and adjust later? Not really. The lunar orbit insertion burn has to happen inside a narrow corridor in time and space. If you start it too early or too late by even a couple of minutes, your position and velocity at the end of the burn don't match the planned orbit. The altitude might come out much lower or higher than intended, and the orbit's tilt relative to the lunar surface can also be off. Fixing that later means more fuel and you don't have a lot of margin. If you miss the burn completely, there is no orbit to fix. You sail past the Moon on your incoming trajectory. At that point, unless you have a ridiculous amount of spare propellant and a plan for a big recovery burn, you have essentially turned the spacecraft into an expensive piece of hardware on a new path around the Sun. There is no atmosphere to naturally slow you down, no air brakes to catch you. Either the engine fires on schedule, or you don't capture. This is where the mission's obsession with timing and procedures pays off. Every step you took from launch through trans-lunar injection and the 3 days of coasting was designed to make sure you arrive at the Moon in a narrow corridor, with the spacecraft oriented correctly, with propellant in the tanks, with the engine ready to ignite. When the burn command is sent, everything that happens in those next 6 minutes is the result of days of work and years of planning. Now let's say the burn works and you're captured. You're in lunar orbit. You might think, great, now we just drop straight down and land. But that's not how Apollo did it, and it's not how serious missions treat a new world. Apollo 11, the first landing, didn't just do a couple of loops and dive in. It completed about 30 orbits around the Moon over the next couple of days. Each orbit took about 2 hours. That time wasn't tourism, it was work. The crew and mission control used those orbits to get precise tracking data on the spacecraft, to map and verify the planned landing site from close range, to test communications when the spacecraft went behind the Moon and out of contact with Earth, and to rehearse what would happen if they had to abort the landing at any stage. Even if you only did, say, 10 orbits, that's already around 20 hours. Double that and you're eating up almost 2 full days just circling, watching and checking. The mission clock keeps running, you're still using life support. Your consumables are still ticking down, but this time is what turns a blind landing into a controlled, understood operation. So why not just cut most of that out and go down quickly? Why not do only 1 or 2 orbits and then descend? The Moon's surface looks clean and simple from far away, but up close it's brutal. You have craters, boulder fields, slopes and shadows. The gravity field is not perfectly smooth either. The Moon has regions of higher density under the surface called mascons, mass concentrations, that tug on the spacecraft in slightly odd ways. They can distort orbits over time, changing low-altitude passes in ways that are small but important. On top of that, your communication with Earth isn't constant. As you orbit, there are periods when you are on the near side with line of sight to ground stations, and periods when you swing behind the Moon and disappear from radio contact. You need to know how your systems behave in both situations. If something goes wrong during landing, you need a good picture of how your orbit behaves, where your ground tracks fall, and how fast you can react when you come back around into contact. Those extra orbits buy you situational awareness. They give you repeated looks at the landing area under different lighting conditions. They let you refine your navigation solution using tracking data from multiple passes. They let you test procedures for aborting a landing and re-rendezvousing with the command module. Yes, they cost time, but they increase the odds that when you finally commit to dropping out of orbit, You're doing it with real knowledge instead of guesswork. By the time all of that is done, and you're parked in a clean known orbit around 100 kilometers up ready to send the lander down, your mission clock has moved a lot. You're roughly 80 to 90 hours past launch, in the range of 3.5 days. In that time, you've gone from sitting on a pad under Earth's atmosphere to low Earth orbit, to a 3-day transfer to a high-speed arrival at the Moon, to a precise braking burn into lunar orbit, followed by dozens of circuits around this airless world. You're now in a place that used to be just a bright disk in the sky, and you're close enough to see mountains, craters, and shadows in real time out the window. But here's the key truth for your original question. Even now, almost half of your round-trip mission time is still ahead of you. You haven't landed yet. You haven't done any real surface work. You haven't started the journey home. So the next step raises the stakes again. Because getting into orbit is one thing, but dropping out of orbit and heading for the surface with limited fuel and no atmosphere to help you is a completely different level of risk. The question now is, how do you take a spacecraft that's circling the Moon safely every 2 hours and deliberately throw it out of that safe orbit toward the ground, knowing that you have only minutes of engine time to avoid either crashing or running out of fuel? How do you land on a world with no air, no runway, and almost no second chances, when the only way down is to deliberately throw yourself out of a perfectly good orbit? Up in lunar orbit, you're safe for now. You're looping around the Moon at roughly 100 kilometers altitude, about 60 miles up. To land, you purposely break that safety. The lunar module does a deorbit burn, a short engine firing that lowers the low point of its orbit so that the new path actually intersects the surface near the planned landing site. That burn has to happen at a specific point in the orbit at a specific time, so that your new trajectory brings you down where the lighting, terrain, and communications all line up. You don't have much fuel. The descent stages on Apollo had tight margins, so the entire descent profile is tuned down to seconds and meters. For Apollo 11, once that deorbit maneuver was done and the powered descent really began, the clock was harsh. From about 15 kilometers up, around 50,000 feet down to touchdown, the powered descent lasted on the order of 12 minutes. That's 12 minutes to kill most of your horizontal speed, control your vertical fall, line up with the landing zone, dodge hazards, and stay within the limits of the engine and the guidance system. Every second you burn is propellant gone forever, and every second you delay a decision can turn a safe landing into a forced abort. Dropping your orbit is the easy part. The real fight starts once you're riding that fall and trying to stay in control all the way down. In powered descent, the lunar module's descent engine has to do everything at once. It can throttle across a wide range, from tens to hundreds of kilonewtons of thrust, and the computer is constantly adjusting that throttle to manage your vertical speed and horizontal velocity together. You're not just falling straight down, you're coming in with a lot of sideways motion that has to be bled off while you descend. On board, the guidance computer is tracking your position and predicting where you'll touch down if you keep your current throttle and attitude. That predicted point, the landing ellipse, shifts with every tiny change in thrust or attitude. The astronauts are watching fuel, altitude, fluid, and computer messages, while also looking outside for rocks, craters, and slopes that weren't visible from orbit. Even small delays in responding to warnings eat into fuel. There is a hard bingo fuel point where, if you haven't landed, you have to abort and climb back to orbit. Those famous 1201 and 1202 alarms on Apollo 11 popped up right here in the middle of descent. They were computer executive overflow warnings, basically saying the guidance computer was overloaded with tasks. No one wanted to see that during the most critical 12 minutes of the mission. Mission Control had seconds to interpret what those codes meant, decide if the guidance was still trustworthy, and give the go or abort call. If that call had gone the other way, Apollo 11 would have had to climb back to orbit, and the first landing would have been scrubbed, all because of timing and computing load in this tiny slice of the mission. So when the dust finally kicks up and the engine throttles down to near zero, you might think the pressure breaks. It doesn't. It just shifts. Touchdown is not the end of the timeline. is the start of a new risk profile. Once the lunar module is on the surface, mission planners have built in hours of checks before anyone goes outside. For Apollo 11, they landed at 2017 UTC, and the first step onto the surface didn't happen until almost 6.5 hours later. In that gap, they were running through post-landing checklists, securing system, configuring the cabin, and making sure nothing was damaged or drifting out of limits. The mission clock never pauses for historic moments. Life support is still running, batteries are still discharging, thermal control is still working against a brutal environment, and the crew is still accumulating fatigue and radiation dose. Every extra hour spent on the surface shifts your timetable for ascent, rendezvous, and re-entry. Windows for leaving the moon and hitting Earth's atmosphere correctly are not infinitely flexible. If you slide your surface schedule, you're quietly borrowing margin from the return leg. That brings you to the main lever you actually have over total mission length. How long do you choose to stay on the moon? Apollo 11's total surface stay was about 21.5 hours, just under a full day. In that time, they did one EVA. About 2.5 hours of walking outside, collected samples, deployed a few instruments, planted the flag, and then climbed back into sleep and prepared to leave. Later missions, once NASA had more confidence, pushed much harder. Apollo 15, 16 and 17 had multiple moonwalks, and Apollo 17 spent around 3 full Earth days on the surface, roughly 75 hours, using a rover to travel kilometers away from the lander. Those extra days on the moon didn't change the distance to Earth at all, but they changed the mission's total duration by several days. What was an 8-day there and back mission became something closer to 12 or 13 days. To pull that off, planners had to budget more oxygen, more water, more food, more battery energy, and more contingency for delays. The more greedy you are with science and exploration time, the more your round trip grows, and the more you tighten the margins on the way home. So when you ask, how long would a moon trip really take, you're partly asking, how much are you willing to do once you actually get there? A quick flag and footprint style mission sits in the shorter end of the band. A serious geology mission with multiple EVAs and a rover pushes you toward the upper end, even if the flight times to and from the moon barely change. Now look at the mission clock at the moment that really lives in everyone's head, the first human step onto the lunar surface. By the time that happens, you're roughly 100 hours or more into the mission, over 4 full days since launch. You've already burned half your round-trip time budget just getting here and stopping. You have survived launch, orbital insertion, trans-lunar injection, 3 days in deep space, a high-stakes braking burn into lunar orbit, and a 12-minute powered descent to the surface. Earth is now a small, bright sphere in the black sky, not the ground underneath you. And here's the uncomfortable truth that drives everything after this. At this halfway point in the mission timeline, you are standing on another world with the entire return journey and all its burns, rendezvous, and re-entry still ahead of you. Every extra hour you spend on the surface from now on, you pay for twice, once in consumables used now, and once in safety margin you'd like to have on the way back. So the question that tightens the tension for the next phase is simple. After all this effort to land, how do you decide when it's time to stop exploring, climb back into a tiny ascent stage, and trust a one-shot rocket to get you off the moon at all? How do you know when to stop exploring and leave, when every extra hour on the moon feels valuable but also quietly eats into your chances of getting home in one piece? On the surface, your biggest enemy isn't craters or rocks, it's the invisible countdown built into your life support. Oxygen, water, food, battery charge, CO2 scrubbers, all of it is finite, and all of it is planned with margins, not miracles. The Apollo lunar modules carried consumables meant for roughly 2 days of surface operations, give or take, assuming nothing major goes wrong. If you want to push past that, you're into careful rationing, backup tanks, and contingency plans. Every hour you spend doing geology, taking samples, or deploying instruments is 1 more hour closer to hitting those hard limits. The cooling system keeps your electronics and your suits in the right temperature range, but its pumps and radiators also draw power. The CO2 scrubbers in your suits and the cabin can only absorb so much carbon dioxide before they saturate. Even simple things like heating water for food and managing humidity use up both energy and consumables. So when mission planners say you get this many hours of EVA, this many hours of sleep, this many hours of prep, it isn't arbitrary. It's the best fit they can find between do real science and don't find out what happens when the oxygen margin disappears. If life support is one ticking clock, what's the second one that quietly limits how long you can stay in one spot? That's the power and lighting environment set by the moon's slow rotation. The moon takes about 27.3 Earth days to spin once, so from a fixed point on the ground, you get around 14 Earth days of sunlight and 14 days of darkness. Apollo missions chose landing times very carefully. They went down during local lunar morning when the sun was low on the horizon. That low sun angle throws long shadows, making rocks and craters stand out clearly. But it's also not yet the brutal thermal peak of lunar noon. If you hang around too long, the local time moves toward midday. Surface temperatures climb above 100 degrees Celsius, around 212 degrees Fahrenheit. That's boiling water level heat, hitting a surface with no air to buffer it. Your suit cooling system and the lander's thermal control suddenly have to work much harder to keep everything within safe limits. Pumps get hotter, radiators run less efficiently, and every watt of electrical power used for cooling is power that isn't available for instruments or communication. Extend that situation long enough, and you risk overheating hardware, shortening its life, or forcing early shutdowns of systems you'd prefer to keep running. So your when do we leave decision isn't just about oxygen and food, it's also about where the sun is and how much more thermal stress your gear can tolerate. So you've got life support limits and thermal limits. What's the third, less obvious set of limits that still bites you if you ignore it? Radiation and dust, two things you can't see directly, but that stack up with every day and every EVA you add. The moon has no global magnetic field and no atmosphere. That means the surface is exposed to solar radiation from the sun and to cosmic rays from outside the solar system. Apollo missions kept total mission durations under about 2 weeks, partly to keep radiation doses within acceptable bounds for the crew. On top of that, there's lunar dust. Every time you move around outside, dust clings to your suit, your tools, and your equipment. It's extremely fine, abrasive, and tends to stick due to electrostatic charging. When you come back into the lander, some of that dust rides in with you. Over multiple EVAs, dust gets into seals, joints, and filters. It can scratch visors, wear down moving parts, and if it gets airborne inside the cabin, pose a risk if inhaled. No one wanted to find out what happens if you do 10 or 15 long EV, as in a row with Apollo-era hardware. In practice, that meant there was a practical cap on how many times you went outside and how long each trip lasted. You're not just counting down oxygen and battery time, you're also counting how many times can we get covered in this stuff before something important starts to fail. Now put all of this together and ask the real planning question: what happens if you decide, let's double the surface time? With Apollo-style hardware, doubling the surface stay usually meant stretching the entire mission by days, not hours. More time on the moon means more oxygen, more water, more food, more fuel for the fuel cells or more battery capacity, and more robust life support both in the lander and in the suits. That extra mass has to be launched from Earth, accelerated into orbit, pushed to the moon, and landed. So the ship grows, the rocket load grows, and the risk profile shifts. You can see this in the Apollo record. Early landing missions sat near the 8-day total duration range. As NASA got more comfortable and started demanding more science, missions crept upward. By the time you get to the later flights, like Apollo 17, you're looking at missions that are close to 12 to 13 days total. That extra time isn't because the distance changed, it's because the planners deliberately widened the surface window, adding EVAs, adding rover traverses, and packing in more experiments. So in very plain terms, if you want to do more on the moon, your round-trip answer to how long does it take slides upward. You can't just bolt more science onto the same 8-day plan without paying for it in schedule, mass, and risk. Once you've done everything you plan to do, and maybe a little more, You finally get to the moment everyone forgets to think about the last time you close the hatch. When you climb back into the lunar module after the final EVA, brush off as much dust as you can, and seal the hatch for good. Your surface chapter is over, but the mission certainly isn't. At this point, depending on how aggressive the surface plan was, you might be 5 to 8 days into the mission. That's already more than half of a typical 8 to 12 day Apollo profile. You've spent days running on life support far away from Earth. Your systems have been baked and chilled, your suits and hardware have taken dust hits, and your crew has been working in partial gravity with limited sleep and constant checklists. You've used up a big chunk of your consumables and your psychological margin, and you still have to get off the moon, rendezvous in orbit, fire the engine to head home, survive re-entry and hit the ocean on target. And here's the sharp edge on the timeline now. The next maneuver has almost no forgiveness built into it. The ascent stage on the lunar module is a small one-shot rocket. If it doesn't light, or if it fails mid-burn, there is no second rocket waiting and no rescue ship can reach you. So the tension spikes again, because the question ahead is brutal. How do you leave the surface safely when your only ride back to orbit is a single engine burn that has to work the first time, with almost no backup plan? How do you leave the moon when your only ride off the surface is a single engine that has to work perfectly the first time, with no backup sitting in the garage? The ascent stage of the lunar module is exactly that, a one-shot rocket. All the return to orbit capability is in that small upper section. Once you light its engine, there's no staging drama, no fancy throttling for style. It's a straightforward burn designed to be as simple and reliable as engineers could make it. The goal is clear. Go from sitting on the surface in lunar gravity back up into orbit at roughly 1.6 kilometers per second, a bit over 5,000 kilometers per hour, in about 7 minutes of engine time. If that engine doesn't ignite, or if it dies early, there is no second ascent stage, no spare lander, no rescue vehicle that can reach you in time. This is the burn that decides whether you will ever see Earth directly again. That's why the design is conservative, fewer moving parts, fixed thrust profile, systems checked again and again before you even think about the countdown. When you commit to that ignition, you're betting the entire second half of the mission on those few minutes, but even getting off the surface isn't enough. You can't just blast upward whenever you feel ready and hope to find the command module later. Orbital mechanics doesn't work that way, and your fuel budget doesn't forgive sloppy timing. The timing of lunar ascent is planned down to minutes. The command module is orbiting the moon at a set altitude and period. Your ascent has to launch into nearly the same orbital plane, and with the right phase, so that after you finish your initial climb and maybe complete an orbit or two, your path lines up with the command module's path. If you launch too early or too late by tens of minutes, you end up ahead or behind in the orbit, and fixing that offset costs propellant. Orbital phasing is basically the art of arranging it so that both spacecraft are in the same place at the same time, with a small relative speed. If you get the ascent time right, you can do that with a few well-planned burns. If you get it wrong, you can still fix it, but you pay in extra orbits and extra delta V. Every extra burn eats into the fuel margin you'd rather keep for contingencies. Every extra orbit eats into life support and mission time. So the launch now decision isn't about comfort, it's about making the rendezvous solvable with the limited fuel and time you have. Once you're in roughly the right orbit, the next phase is rendezvous and docking, which looks simple in animations and completely isn't in real life. Orbital rendezvous is a precise sequence of small burns to gradually reduce the distance and relative speed between the two vehicles. You approach in stages, closing from tens of kilometers to a few hundred meters, then down to meters, all while keeping relative velocity under strict limits so that you don't bump hard and damage a docking port. From far away, the docking itself looks like a quick click, two pieces snapping together. On the mission clock, it's hours of approach, burns, range and rate checks, attitude adjustments and alignment. When you finally get a hard dock, you're not done. You have to equalize pressure, open hatches, move the crew across, transfer sample containers, equipment, data tapes and anything else that needs to come home. You also secure what stays behind. Apollo 11, for example, lifted off from the surface on July 21st, docked with the command module a few hours later, and then spent more time stowing samples, reconfiguring the spacecraft, and preparing to discard the ascent stage. None of that is rushed. Every valve position, every latch, every cable is checked, because from this point on, the command and service module is the only vehicle that can bring you back through Earth's atmosphere. Once the transfers are complete, the ascent stage has done its job. There's no reason to keep it attached, and several reasons not to. It adds mass, it complicates centre of mass calculations, and it's a dead system you don't want hanging around during critical burns, so you jettison it. In some missions, those ascent stages were deliberately crashed into the moon so that seismometers on the surface could record the impact and help map the interior structure. Either way, it's gone. Your ride back to orbit is discarded, and you're fully committed to the command and service module. Now everything focuses on prepping that combined spacecraft for the trip home. The command module holds the heat shield, the re-entry shape, the seats, and the main life support for re-entry and splashdown. The service module holds the big engine and most of the propellant for the trans-Earth injection burn and the mid-course corrections on the way back. Before that burn, you run through a thorough set of checkouts confirming the engine is ready, valves respond, guidance is aligned, and tanks and lines are in the right condition. The burn that comes next, the trans-Earth injection, is the lunar mirror of the trans-lunar injection you did 3 days ago. This time you fire the main engine while you're in lunar orbit, adding around 1 kilometer per second of velocity relative to the moon, reshaping your orbit so that it no longer closes around the moon, but stretches out and intersects Earth. This is the push that starts your multi-day fall back into Earth's gravity well. Get the timing and magnitude right, and you arrive at Earth with the correct speed and angle for re-entry. Get it wrong, and you arrive too fast, too slow, or at the wrong place. When you reach this point, back in lunar orbit after ascent, docked, reconfigured, and ready for trans-Earth injection, it's time to look at the mission clock again. Depending on how long your surface stay and your orbital operations were, you're about 6 to 9 days into the mission. Short-stay missions sit on the lower end of that, long-stay science-heavy missions on the upper end. Think about where most of that time has actually been spent. A big chunk was on or near Earth, wrestling your way into low Earth orbit and then into the trans-lunar trajectory. Another big chunk was inside the moon's gravity, circling it, landing on it, working on the surface and climbing back up. You've spent relatively few days in the in-between region, and a lot of days sitting deep inside gravitational wells where burns and timing matter most. The last major phase ahead of you is another fall through that in-between region, this time aimed precisely at one planet and one small slice of atmosphere. You're going to spend about 2.5 days coasting back with only small corrections, and then commit to a re-entry corridor that is only a couple of degrees wide. If you come in wrong, you can skip back out into space or hit the air so hard that the heat load and G-forces exceed your design. So the tension now shifts again. You've finished all the major go-outward burns. The ascent engine has done its one job and is gone. The next big step is the burn that doesn't send you somewhere new, it sends you home, and it has to set you up perfectly for the most violent minutes of the entire mission. The question for the next phase is simple and unforgiving. After spending more than a week bouncing between gravity wells, how do you fall back to Earth in just a couple of days and hit a re-entry path so narrow that a small mistake can mean missing the planet or burning up in the sky? You'd think that after landing, walking around and blasting off the moon again, the real danger would be behind you. It isn't. The next burn you do decides whether you fall home cleanly in a couple of days or show up at Earth's doorstep at the wrong speed, in the wrong place with no good way to fix it. To actually head home, you do the trans-Earth injection burn. You're in lunar orbit, moving around the moon in a closed loop. To break out of that loop, you fire the service module engine again, this time pointing it so that the extra push raises your orbit until it stretches all the way out to intersect Earth's position. You add roughly 1 kilometer per second of velocity relative to the moon, just a few hundred seconds of engine firing. It's short, but the consequences are big. When the engine cuts off, your orbit is no longer a neat circle around the moon, it's an escape path that drops you into Earth's gravity well. For Apollo 11, that TEY burn happened on July 22nd. Once it was complete, the crew was locked into about 57 hours of coasting across cislunar space. No second big engine burn waiting halfway. No stop here and think. Just gravity, a set of small course corrections, and a countdown to a very specific point in space, where Earth will meet them with atmosphere and 11 kilometers per second of relative speed. On the way out, you felt like you were climbing uphill out of Earth's gravity. On the way back, you're doing the reverse. After the TEI burn, the moon's influence fades and Earth's gravity starts to dominate again. You're falling into a deep well. As you get closer, your speed relative to Earth climbs steadily until you're approaching the planet at around 11 kilometers per second, roughly 40,000 kilometers per hour, about 25,000 miles per hour. You're not firing a main engine to maintain that speed. Earth's gravity is doing the work for you. Those 2.5 days of return are, again, mostly about small corrections. The mid-course burns are tiny, measured in meters per second, but they matter a lot. You're not trying to aim for Earth in a vague way. You're trying to hit a thin, invisible slice of atmosphere with the capsule's blunt heat shield pointed exactly in the right direction. Too much change in angle now and you overshoot or come in too steep later. So the timeline on this leg is less about covering distance and more about setting up the exact entry conditions you need. That's where the re-entry corridor becomes the real boss fight. You can't just dive into the atmosphere at any angle that touches air. If you come in too shallow, the capsule skims the upper layers, decelerates a bit, but doesn't lose enough speed. You bounce back out on a longer stretched path that could leave you in a high decaying orbit or send you around for another pass. That's extra radiation, extra mission time, and serious heating over a longer period. If you come in too steep, the opposite happens. You hit dense atmosphere too fast. The heating rate spikes, the thermal load on the heat shield jumps, and the G-forces on the crew can climb into levels that are dangerous or at least punishing. Instead of something like 4 to 7 G for a short period, you risk much higher transient loads and a heat environment your materials weren't tested to survive. For Apollo, the safe entry corridor was only on the order of a couple of degrees wide in an entry angle. That means the difference between too shallow and just right and too steep is a small tilt in the trajectory, but with massive consequences. The last mid-course correction burn, usually done many hours before atmospheric entry, is tuned specifically to drop the capsule into that narrow slice. After that burn, you mostly leave it alone. There's no big engine to fix major mistakes later. The attitude control thrusters can tweak orientation, not radically change the path. Then comes the part everyone has seen in footage, but almost no one thinks about in timing terms. From the moment the capsule first brushes the upper atmosphere to the moment the parachutes deploy and you hit the water is only minutes. In that short time, the capsule converts enormous kinetic energy into heat and deceleration. The plasma sheath blocks radio communication for a while, giving you a communications blackout window where mission control just watches the clock and waits for the signal to come back. When the air has done its job and the capsule has slowed enough, the parachute sequence starts. Drogue shoots to stabilize, then main shoots to slow the descent to a safe splashdown speed. Altitude, speed, and timing all have to be within bounds for each step. You don't get to rerun the sequence if something misfires. The final impact with the ocean is relatively slow in speed terms, but after 8 to 12 days in space and a few minutes of blazing re-entry, it's still a serious event for the crew and the structure. For Apollo 11, splashdown happened at 12:50 p.m. Eastern Daylight Time on July 24th in the Pacific Ocean. Officially, that's the mission end point in a lot of timelines, but practically, you still have hours of work left. Recovery forces in ships and helicopters move in, secure the capsule, extract the crew, and bring them aboard the carrier. Only when everyone is safely on deck, breathing normal air under normal gravity, does the mission really feel complete. Look at the full door-to-door picture now. For an Apollo-style landing mission, your total time from launch to splashdown sits around 8 to 12 days, depending on how long you stayed in lunar orbit and on the surface. Short missions with minimal surface time are near that 8 to 9 day mark. The longer, science-heavy missions push toward 12 to 13 days. The travel legs themselves, Earth to Moon and a Moon to Earth, are each only a few days. The rest is orbit operations and surface work. And that gives you the real grounded answer to the question we started with. With 1960s and early 1970s chemical rockets, Apollo navigation and life support tech, going to the Moon and coming back on a real crewed mission takes on the order of 8 to 12 days. Not a casual commute, but not some multi-month odyssey either. It is surprisingly close to what we would still plan today with modern hardware, because the physics, the safety limits and the life support constraints haven't changed. So here's the tension that sets up everything about faster or shorter missions if we can already cross the Earth-Moon gap in a few days, and the round trip sits in the range of a week and a bit. What actually stops us from crushing that into a one-day sprint there and a one-day sprint back? You might look at that 3-day cruise to the Moon and think, alright, just push harder, make it one day there, one day back, problem solved. But once you start running the numbers, you find out very quickly that space does not reward just go faster thinking. It punishes it. First problem, energy. To cut the trip time in half, you don't just bump the speed a little. The transfer orbit changes shape, your required change in velocity, your delta V, jumps by several kilometers per second. And the rocket equation is brutal here. Every extra kilometer per second you want means you need a much larger ratio of fuel to payload. That doesn't scale linearly, it grows in a nasty exponential way. If a 3-day transfer already needs a big booster to give you roughly that 10.8 kilometers per second departure speed from Earth, pushing that to the kind of speed you'd need for, say, a 1-day transfer could mean adding multiple kilometers per second on top. That sounds small on paper, but in rocket design it's the difference between hard but buildable, and this vehicle is now mostly fuel tank with a tiny capsule on top and a price tag that makes no sense. You don't just double your launch mass, you can end up multiplying it, and with it, complexity, failure points and cost. So even before you think about people inside, the physics is telling you, cutting time aggressively costs you a lot of propellant and a lot of hardware. Then you layer humans on top of that. New Horizons, for example, left Earth at around 16.3 kilometers per second relative to the Sun, way faster than an Apollo stack. If you want crewed vehicles in that ballpark, you have two options, neither of them friendly to human bodies. You either accelerate very hard for a short time, which spikes the G-load, or you burn for a very long time at moderate thrust, which demands huge propellant mass and big stages that are hard to get off the ground in the first place. Humans can typically tolerate around 3 to 4 G for several minutes, like a tough roller coaster but sustained. Short spikes up around 8 to 9 G are survivable, but only for brief moments and not something you want to build into a normal mission profile. Go beyond that, and you start messing with blood flow to the brain. You risk loss of consciousness, vision issues, and long-term damage. You can't treat astronauts like artillery shells. The acceleration profile has to respect human limits, and that constrains how rapidly you can change velocity. So now you have a rocket equation that hates your fuel demands, and a human nervous system that hates your acceleration ideas. You're still not done with the problems. Next, think about re-entry. Apollo was already coming back at about 11 kilometers per second relative to Earth. That was enough to generate intense heating, plasma around the capsule, and heat loads that pushed crews hard on the way down. Thermal loads scale roughly with the square of velocity, meaning if you double the speed, you don't double the heating, you more than quadruple it. The structure and heat shields suddenly have to survive a massively larger energy dump in a similar or shorter amount of time. In Earth terms, going from 60 miles per hour to 120 miles per hour doesn't just double the crash energy, it ramps it up by a factor of 4. The same kind of scaling hits your heat shield. If you design a mission that aims for a superfast transit and comes back at, say, something well beyond that 11 kilometers per second mark, your heat shield isn't just a bit hotter, it's in a completely different regime of material performance. You'd need new ablative materials, stronger structures, more mass in the shield, and even then you're stacking risk for marginal gains in calendar days. Then there's navigation. A tiny angle error at moderate speed gives you a miss distance you can clean up with a correction burn. The same tiny angle error at much higher speed, over hundreds of thousands of kilometers, turns into a huge positional miss, maybe thousands of kilometers off target when you're trying to intercept the moon or hit a re-entry corridor. Faster trajectories shrink your timing and angle tolerances. You can't wait as long to make corrections, and when you do, those corrections have to be more precise and sometimes more powerful. That means you need better everything, not just a bigger engine. You need more accurate guidance systems, higher precision star trackers, more stable inertial measurement units, better ground tracking, more capable computers, and more robust communications. You need long, clean tracking arcs from ground stations so that you can refine the trajectory earlier. If your navigation solution isn't razor sharp, a high-energy fast transfer actually increases your chance of missing your target, not reduces it. So by the time you add it all up, the picture is clear. To turn a 3-day transfer into a 1-day sprint for humans, you're not just buying extra fuel. You're buying a heavier rocket, harder engineering, tougher thermal protection, tighter navigation, more demanding ground support, and much worse consequences if anything fails. The entire system gets pushed closer to its limits. This is why crewed moon missions settle into a comfortably fast regime instead of chasing record times. A few days of cruising between Earth and Moon is already very fast by human standards, but it keeps the G-loads in a manageable range, keeps re-entry heating inside what proven materials can handle, and gives you enough time to detect and correct small trajectory errors without panicking. It also fits with realistic launch vehicle sizes and budgets. And that's why even with 21st century tech, the planned timelines for crewed lunar missions still live in the multi-day band, not in the hours band. Yes, our guidance computers are better, our simulations are stronger, and our materials have improved, but the core constraints, rocket equation, human tolerance, heating, and navigation at high speed have not magically disappeared. So the next logical question is this: if physics allows machines to blast across the Earth-Moon distance in hours, and humans are locked into this 8 to 14-day round-trip band, what happens when you take people out of the equation and just send robots instead? How far can you push the timeline when you don't have to worry about hearts, lungs, and re-entry couches? Here's the twist that really breaks your gut feeling about how long it takes to get to the moon. Machines have already crushed the 3-day benchmark so hard it's almost a joke, and also stretched it out so far that a human crew would mutiny. On the far side, the record is held by a spacecraft that wasn't even going to the moon. New Horizons, the Pluto probe, crossed the distance of the moon's orbit just 8 hours 35 minutes after launch. It left Earth on a hyperbolic escape trajectory, not a bound orbit, screaming away at about 16 kilometers per second relative to the Sun, far beyond normal Earth orbit speeds. No life support, no fragile crew, no need to slow down at the moon, no need to enter orbit, land, or ever come back. Just go as fast as the rocket and trajectory design allow, and don't worry about re-entry heating, G-comfort, or abort modes. That's why it could go so absurdly fast. When you strip away all the constraints that protect human bodies and reuse, you can aim for pure energy and let the vehicle leave the Earth-Moon system entirely. You're not doing a round-trip moon mission at that point. You're doing a one-way, high-energy solar system shot that just happens to blitz through lunar distance in under a workday. On the opposite extreme, robots also show you how slow you can afford to be when no one on board needs food, sleep, or a quick ride home. Take missions like Chandrayaan-2 and Chandrayaan-3. Instead of one big brutal burn to go straight from low Earth orbit to the moon, they used a series of orbit-raising maneuvers. You start in a low orbit, fire the engine a bit at perigee to raise the far side of the orbit, circle again, repeat. Each loop gets more stretched, each apogee higher, until eventually your path reaches the moon's distance and the moon's gravity can take over. That sequence takes weeks. Chandrayaan-2 needed on the order of 48 days to get into lunar orbit. Chandrayaan-3 was in the same rough multi-week regime. From the spacecraft's point of view, that's fine. The electronics don't care if they fly for 6 days or 60 days, as long as the power system and thermal design are built for it. From a human point of view, every extra day means more water, more food, more oxygen, more radiation exposure, and more ways small failures can add up. So robotic missions can trade time for fuel very aggressively, while human missions cannot. Even among robotic missions, not all profiles are equal. A pure orbiter can afford to do gentle insertion burns and then spiral slowly downward over time to lower orbits. That spreads out the energy and saves propellant, at the cost of a long, drawn-out timeline. A lander has a tougher job because it has to do a precise braking burn to get from orbit to the surface without turning into debris. A sample return mission has the hardest task set of all. It has to land softly, collect material, then launch back off the moon and send that material home. China's Chang'e 5 is a good example. It flew to the moon, entered orbit, separated a lander, touched down, scooped samples, launched those samples back into lunar orbit on a small ascent vehicle, docked with an orbiter, and then sent the return capsule back to Earth. That is a lot of separate maneuvers. Even with no crew, the full loop of material leaves Earth, lands on Moon, comes back and lands on Earth, still lives in the week-plus time frame. Moving rocks, not people, still doesn't make it instantaneous, because the physics of landing and launch just don't get easier. So when you see an 8.5 hour to lunar distance record and a 1 to 2 month slow spiral transfer in the same era, it's easy to ask the next question. Why not strap humans to the fast hardware and grab the record? On paper, you could try. You could design a New Horizons class booster with a crew capsule on top, blast a human crew out toward the moon in under a day, and then slam on the brakes with a huge capture burn, or skip capture entirely, do a high-speed flyby, and try to survive an even more nastier re-entry back at Earth. In practice, that's not just a little bit harder than Apollo. It's so extreme that it starts looking harder than a carefully designed Mars mission. You'd need life support that can handle crazy accelerations and potentially very high re-entry speeds. You'd need a heat shield built for a much more violent energy dump than Apollo ever saw. You'd need navigation performance and correction capability far beyond comfortable missions, because your timing and angle errors would have almost no slack. And all of that for what? To shave a couple of days off a timeline that's already short on a planetary scale, while multiplying risk and cost. That misses the entire point of human moon missions. The goal is not to beat robotic speedruns. Robots are always going to be better at that. The goal for crewed flights is to put people where they can think, react, explore and fix things, with safety margins that aren't razor thin every second. You want a mission that can survive glitches, not a stunt that falls apart if one sensor blinks. So robots stretch the range of time to the moon in both directions. On the fast side, they show you that with enough energy and no return requirement, you can cross the Earth-Moon distance in under 9 hours. On the slow side, they prove that if you're patient and efficient with fuel, you can take 1 to 2 months and still get the job done. With today's technology, that gives you a rough theoretical window of about 8 hours to maybe 2 months for trips that interact with the moon in some way. But as soon as you add humans, that wide window collapses into a narrow, very familiar band. Life support, G-limits, radiation, re-entry heating, abort options, and realistic rocket sizes all shove you back into the same region Apollo lived in, roughly 8 to 14 days for a full round-trip landing mission. A bit shorter if you barely stay, a bit longer if you do serious surface work. And that sets up an important question for the next era. If we already know that robots can push the extremes, but humans are locked into this multi-day band, what happens when we look at our new generation of moon missions, Artemis, Gateway, reusable landers? Are they actually faster? Or are we about to spend even more days in cislunar space on purpose? You'd probably expect that with new rockets, new computers, and 50 years of experience, our modern moon missions would be a lot faster than Apollo. Shorter timelines, tighter profiles, slicker everything. But when you look at Artemis, the first thing you notice is almost the opposite. Modern does not automatically mean shorter. It often means we added more steps on purpose. Start with Artemis 1, the first big test of the Space Launch System, and the Orion capsule in 2022. No crew, just the rocket and the spacecraft doing a full-up rehearsal. That mission didn't do an Apollo-style quick loop. It took about 25.5 days, more than 3 weeks to launch, swing past the moon, hang out in a distant retrograde orbit, and come back to Earth. That's more than double the duration of most Apollo landing missions. And that was not a mistake, it was deliberate. A longer flight gave engineers time to stress test Orion's systems, check the life support hardware over many days, push the power systems, validate navigation in deep space, and then hammer the heat shield with a high-speed re-entry after a long coast. The point was not, how fast can we repeat Apollo? The point was, how hard can we push this new system and see where it creaks? So right away, Artemis 1 tells you something important. Newer missions are often longer because we're testing more, not because we forgot how to go fast. Now look at the crewed missions, Artemis 2 and Artemis 3. These are not going to be 2 or 3 day stunts. The planning numbers are already in the 10-day plus range. That includes multiple days in lunar orbit, time for checkout, and possibly several days docked to a lander or near the surface. The cruise legs between Earth and Moon still sit in that familiar few-day band, roughly 3 days out and a few days back, but the total mission grows because of what happens in between. Mission designers spread the timeline on purpose. They want more time for rendezvous and docking operations, more time to verify that every system is stable before committing to critical burns, and more time for actual science and exploration near the Moon. If you're going to spend billions of dollars and take on the risk of a crewed flight, you don't want a touch-and-go profile unless there is a very good reason. You want room in the schedule to react to surprises, and Artemis is not just about single flights. It's built around the idea of a cislunar infrastructure, and that's where the Lunar Gateway comes in. Gateway is a planned small space station in a near-rectilinear halo orbit around the Moon, NRHO for short. That orbit is weird compared to a simple 100-kilometer circular lunar orbit. It's stretched, tilted, and takes you far above the Moon on each loop. It's chosen because it is relatively stable, gives good line of sight to both Earth and large parts of the lunar surface, and works well as a staging point for different landers going to different sites. The trade-off is time and complexity. Transfers from Earth to an NRHO-like gateway are longer and more complex than a simple Apollo-style dive into low lunar orbit. You may need extra burns, different timing, and more days in transit or loitering. Then to go from gateway down to the surface and back, you're adding more dockings, more burns, and more time in lunar vicinity. A typical go to gateway, go down to the surface, come back to gateway, then return to Earth and mission can easily expand into the 2 to 4 week range, 14 to 28 days. Again, this isn't because we're worse at flying, it's because we're adding more nodes, more vehicles, and more objectives. Reusable landers, logistics modules, long-term experiments, international partners, and cargo runs. Every extra segment adds days. The Moon becomes less of a single trip and more of a network. Could we still design a faster minimalist Artemis-style mission if we wanted to? With SL S-class rockets and modern navigation, yes, you could pick a more aggressive transfer, cut down the time in lunar orbit, do a short surface stay with a tightly controlled timeline, and aim for a total duration closer to the lower Apollo range. Technically, it's possible, but that is not what the program is optimizing for. Engineering teams are focused on safety, reuse, and logistics. They want hardware that can fly multiple times, procedures that can be repeated with different crews, and timelines that allow troubleshooting and learning. Shaving a day off the cruise or rushing the orbit phases doesn't help with that. What changes versus Apollo is not the transit time in a big way. It's what you do once you're there, where you go, how many times you go, and how much infrastructure you build and reuse. So if you ask, with Artemis-level tech, how long would it take to go to the Moon and come back on a real mission? The answer doesn't suddenly drop to 3 or 4 days total. It actually sits a bit higher. A realistic crewed Artemis-style mission, with time in lunar orbit, time at gateway, and at least a short stay near or on the surface, is going to live in roughly the 10 to 20 day range. On the low end, you might have a simple orbital mission that loops around, tests systems, and returns without a long surface visit. On the high end, you could have a gateway-based mission, with several days of surface work, multiple dockings, and extended checks. Either way, you're still talking a couple of weeks as the natural scale for a full round trip, not a single day or one long weekend. And that brings up the next uncomfortable question. If modern programs still live in this 10 to 20 day band, and if cutting time drastically is so expensive, Is there any propulsion technology that could actually bend this clock in a meaningful way without breaking everything else? Or are we locked into this timescale until we invent something completely different? When you hear about new propulsion ideas, it's easy to think, alright, once we get nuclear rockets or something exotic, the moon will just be a quick hop. The reality is a bit less dramatic. Better drives bend the timeline. They don't delete everything that makes a mission hard. Start with nuclear thermal rockets, NTRs. Instead of burning chemical fuel to make hot gas, you use a nuclear reactor to heat a propellant, usually hydrogen, and push it out the nozzle. The key metric here is specific impulse, basically how efficiently your engine turns propellant into thrust. Nuclear thermal designs promise roughly double the efficiency of the best chemical engines. In simple terms, for the same mass of propellant, you get about twice the change in velocity. That doesn't turn your moon mission into a relativistic sprint, but it does change your options. With an NTR upper stage, you could pick a faster transfer to the moon without your rocket size exploding into something ridiculous. You could, for example, shave some hours or maybe even a day off the transit, or carry more payload for the same total delta V budget. You might choose steeper departure paths, more aggressive braking profiles, or more flexibility in launch windows because you have more speed budget to play with. But even at double efficiency, you're still operating under the same basic constraints. The rocket equation still bites. You still have to control G-loads. You still have to handle a high-speed re-entry at Earth. Nuclear thermal propulsion gives you more breathing room in design. It doesn't give you magic. Then there's electric propulsion, which is almost the opposite in behaviour. Ion engines and Hall thrusters don't burn propellant explosively at all. They use electric fields to accelerate ions to very high speeds, getting insanely high specific impulse. They can run for months or even years, slowly adding up a huge total velocity change with tiny propellant mass. That sounds perfect until you remember the word slow. The thrust is tiny, often measured in millinewtons, thousandths of a newton. That's basically the weight of a paperclip in Earth gravity, or less. You can't lift a crewed spacecraft off Earth with that. You also can't do quick high-G burns to escape a gravity well or hit a re-entry corridor. So electric propulsion is great for cargo, terrible for launch and most human maneuvers. What you can imagine, realistically, is a split architecture. Humans ride fast chemical or nuclear thermal stages for launch, capture and re-entry, the big, violent maneuvers. Cargo tugs with ion engines or Hall thrusters move supplies, fuel and infrastructure between Earth orbit, lunar orbit and maybe gateway, over multi-week or multi-month spiral trajectories. Your habitats, your spare parts, your fuel depots might crawl around cislunar space on an electric propulsion, while your crew transfer systems do the fast hops. Then there are the really exotic ideas people like to talk about. Fission fragment rockets, fusion drives, beamed power sails, all the speculative stuff. On paper, designs like that can reach specific impulses and thrust levels that would make Earth-Moon trips take hours or even minutes. You fire up a fusion drive, push hard, flip halfway, brake hard, and you're there in a fraction of the time. But right now, that's paper, not a hardware. We don't have operational fusion drives, we don't have practical beamed propulsion systems that can safely accelerate a crewed vehicle to crazy speeds and then decelerate it again without missing the target. The same way you can design a warp drive on a whiteboard by writing down equations that look nice, you can design a 1-hour moon commute. Actually, fielding that as flight-ready hardware is a completely different level of difficulty, and we're not close. Here's the irony that people miss. Any propulsion technology strong enough and mature enough to make the moon a 1-hour commute would do far more than that. If you can cross 384,000 kilometers in an hour or two with a crewed ship, you've just turned Mars into a trip of a few days instead of months, and made the outer planets reachable in practical mission times. At that point, the moon stops being the big destination and turns into a convenient stepping stone, maybe a refueling site or construction yard. So from a long-term perspective, the moon is not the bottleneck, it's a test case. Once you unlock truly extreme propulsion, your focus shifts outward fast. You don't build god-tier engines just to shave 48 hours off an already short flight if those engines can carry you across the solar system. And that brings us to the real bottom line. Even as technology improves, the underlying physics and safety constraints don't go away. Orbital mechanics still sets where and when trajectories line up. Re-entry heating still scales hard with speed. Human tolerance for GE and radiation doesn't magically expand. Better drives let you push closer to those limits, but they don't erase them. So what does a realistic fast near-future crewed moon mission look like if you give it nuclear thermal upper stages or very optimized chemical stages, plus modern navigation and materials? You might compress some of the slack out of the schedule. Maybe your transfer legs get trimmed by part of a day each. Maybe you design a shorter surface stay for a specific high-priority objective. In that case, a fast and lean round trip could live in something like the 5 to 10 day range. That's faster than the longest Apollo or Artemis style profiles, but still nowhere close to 5 hours there, 5 hours back. Because by the time you try to crush the mission down into hours, you're fighting the rocket equation, human biology, thermal limits, and navigation precision all at once. Which leaves you with one last very practical question to answer. If the physics and the tech keep pushing us into roughly the same band, what does an actually realistic, stripped down but modern moon mission look like on the clock step by step from launch to splashdown? So after all this, if you're actually on the spacecraft, what would the clock on your mission timeline really look like? Not in vague about a week or two terms, but phase by phase as start to finish. Take the simplest realistic case first, minimal crewed landing mission using something in the Apollo or Artemis class. Not a stunt, not a speed run, just a lean, well-planned flight where the goal is land, do a solid amount of work, get home with margin. You light the rocket, you fight your way through the atmosphere, and you get into low Earth orbit. That launch plus parking orbit phase is only around 0.2 days on the clock, a few hours total. The wild thing is, in that tiny slice of time you've already burned most of the propellant and paid most of the energy cost, but in timeline terms, you've barely started. From there, you perform trans-lunar injection and begin the 3-day coast. That's the big chunk, roughly 3 days from leaving low Earth orbit to arriving at the moon's neighbourhood. During that time, you're doing navigation checks, mid-course corrections, system monitoring, and dealing with all the human factors of living in a small cabin in microgravity. The calendar moves, the engines mostly do not. When you reach the moon, you slam on the brakes with the lunar orbit insertion burn and settle into orbit. In a minimal mission, you might only spend about half a day to a full day in lunar orbit before landing. So call that 0.5 to 1 day. That time is used for checking systems, confirming the landing site, and making sure you're not about to land into a crater or a communications dead zone. Then you drop out of orbit in the lander. A short controlled descent, a landing, and a tight surface schedule. For a stripped down profile, give yourself roughly 1 Earth day on the surface total, about 24 hours. That's enough for at least 1 EVA, deploying some instruments, collecting good samples, and sleeping once in 1/6 gravity. But you're not treating the moon like a long-term field camp. You're in, you work, you leave before the margins get thin. After that, the return chain starts. Ascent from the surface, rendezvous with the orbiter, docking, transfer of crew and samples, and the trans-Earth injection burn. All together take on the order of half a day, around 12 hours. It feels like a lot of activity, but on the mission clock, it's a single chunk. Once you're on the way home, you're in another coast phase, this time about 2.5 days. You fall back into Earth's gravity well, your speed climbs toward that 11 kilometers per second mark, and you spend your time refining the trajectory so that you hit the re-entry corridor properly. It's not idle time, but it is again dominated by monitoring and corrections, not big burns. Finally, re-entry and recovery, the violent endgame. The actual dive into the atmosphere and parachute descent is minutes, but if you include post-landing operations, recovery by ship or helicopter, and the process of getting everyone safely inside a controlled environment, you're looking at roughly 1/10 of a day, a couple of hours, before anyone can say the mission is truly over and the capsule is secure. Add that all up, 0.2 days for launch and LEO, about 3 days out, 0.5 to 1 day in lunar orbit, about 1 day on the surface, 0.5 day for ascent, rendezvous and TEI, about 2.5 days home, and 0.1 day for re-entry and recovery. That stacks into something like 7 to 9 days door-to-door for a realistic but minimal crewed landing mission where you don't get too greedy with surface time. Now, change just one parameter. Your ambition for what you do while you're there. If you add more orbits for detailed mapping, more time for systems checks, and stretch the surface stay from 1 day to about 3 days, the rest of the pattern stays roughly the same, but the total mission length jumps. Those extra 2 days on the surface plus the added margin around them push you into the 10 to 14 day range. That's exactly where the longest Apollo missions lived. And it's where crewed Artemis landings are expected to sit once you fold in gateway operations, more complex landers, and heavy science workloads. So, a flag and reel geology mission, where you're not just proving you can land, but actually doing serious fieldwork, naturally grows into that 10 to 14 day band. You didn't change the distance to the moon. You didn't change the transit time much. You changed what you do in orbit and on the ground, and the timeline followed. How does that compare to normal life, to something your brain understands? If you're aggressive with airline bookings, you can fly commercially from one side of Earth to the other and back in about a day with tight connections. That's your basic high-speed global loop. A moon mission, even the minimal one, is more like stacking a week-long business trip on top of an intercontinental flight that happens at around 11 kilometers per second through vacuum instead of 900 kilometers per hour through air. In distance terms, you're not just doing one straight line out and back. Your trajectories are curved, shaped by orbits, burns, and gravity wells. When you add up the real path length, not just the raw Earth-Moon distance, your round-trip track can be close to 1 million miles, on the order of 1.6 million kilometers. That's like driving the length of the United States coast-to-coast highway system several hundred times, somewhere beyond 300 full cross-country runs, all rolled into a single mission. So when someone asks for the short version, this is the line you put on the thumbnail, and in the description, on a real, modern crewed mission, going to the moon and coming back will take you about 8 to 14 days, and the main thing that moves that number is how long you decide to stay and work there, not how brutally fast your rocket launches. And that's the real shift in perspective. The moon is no longer a mythical destination that demands multi-year odysseys. With current technology, it's a place you can visit on something that looks, from a calendar standpoint, like a 2-week assignment. It's still harsh, airless and dangerous, but fundamentally it's commutable. You can go there, do real work and come back within the same time frame as some Antarctic expeditions or tough offshore deployments on Earth. The strange part is what actually controls that schedule. It's not warp drives, not magical future engines, and not some hidden speed limit in space. It's logistics, it's life support. It's how many days of oxygen, water and food you're willing to carry. It's how much radiation dose you'll accept. It's how much margin a mission planner is willing to leave between we're fine and we're cutting it too close, while staring at a timeline full of burns and windows that do not move just because humans want them to. So the final question, the one that really matters once you understand the clock, isn't, can we get there quicker? It's this. Now that a round trip to the moon fits inside a 2-week mission, what happens to our world when going to another world starts to feel less like a fantasy, and more like a very intense, but very real commute? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.